Videos for volume control CMV with dual targeting, I'm going to be using the Draeger Oxylog 3000 Plus simulator. And the reason I'm using this because with my other ventilators like my V500 and my Vita series, the pressure limiting function is kind of hidden in the back menus and it's very rarely turned on. However, with the Oxylog and my anesthesia machines, the functionality is kind of built in right with the settings. So as you can see, there's not a separate mode. Here's all my modes. I'm going to move my cursor around, and I'm currently using volume control CMV, but there's not a mode tab that specifically says with a dual targeting scheme or Pmax. So with this setting, if we look down at these set points, I have tidal volume, respiratory rate, Pmax, and FiO2. So this Pmax actually turns my volume control CMV into that dual targeting scheme. So it's more of an augmentation to my volume targeting modes to make it a dual targeting scheme. And we can look at the monitor values here, the waveforms, and as you notice this dashed line here, this is actually my Pmax setting, and I'm just going to turn this down a little to 30 for my scenarios, and you can see I brought the 30 down, the pressure down to 30.
Here are the three goals of mechanical ventilation. Let's look at each in more detail. First, safety. Within safety, there are two main objectives. One is to optimize the ventilation perfusion of the lungs, and second, to optimize the pressure volume curve. Optimizing the ventilation perfusion of the lungs, there are also two aims. One aim is to maximize the alveolar ventilation. The second is to maximize oxygenation. I will not be talking about this when selecting a mode of mechanical ventilation because pretty much all mechanical ventilators allow for the manual manipulation of FiO2 and PEEP. However, outside the US, there are some modes of mechanical ventilation that automatically adjust the FiO2 and PEEP. Maximizing alveolar ventilation. Does your mode allow for the manual adjustment of minute ventilation parameters? Second, does your mode allow for the automatic adjustment of support in response to changing respiratory system mechanics?
Let's look at our first two aims for maximizing minute ventilation. And does volume control CMV with dual targeting allow for the manual adjustment of minute ventilation parameters, and is there any automatic adjustment behind the scenes of support in response to chaining respiratory system mechanics? Now, as you can see, I do have my set points of respiratory rate and tidal volume, and that allows for me to change my minute ventilation parameters quite easily. Right up front, operator can do this. So nothing new here. And as for automatic adjustment of these parameters, so here's my measured value. Tidal volume is 600, and currently my respiratory rate is, we'll put it at 12. And I'm going to change my patient's lung compliance by changing the patient status down here to ARDS. So that's going to drop my compliance and changed it to 30. And you notice right away we already have a high pressure alarm. We look at our breath. The machine's not doing anything to change the breathing pattern at all. It's trying to still give the same 600 tidal volume, and it's going to still give the same respiratory rate. So the same minute ventilation parameters. It's not automatically adjusting it like a peak inspiratory pressure. However, we do have the Pmax, or the pressure limitation, which I'm going to get more into that. But this really doesn't change my minute ventilation parameters. It will drop my tidal volume, of course.
In regards to optimizing the pressure and volume curve, the aim is to minimize the risk of volume trauma. To minimize the risk of volume trauma, does your mode allow for the automatic adjustment of lung protective limit? And does it allow for the automatic adjustment of tidal volume?
When looking at our other objective with safety, to optimize the PV curve, our aim is to minimize the risk of volume trauma. Now, does volume control CMVd allow for automatic adjustment of lung protective limit? Now, one could argue that by having this pressure limiting, that provides lung protection, and it does. So if my patient's compliance changes, it limits the pressure, and it still giving the breath so I don't have very low tidal volumes. However, this is still, there's no automation in this at all. This is still operator input. They have to turn this up and down and set it appropriately. So there is no automatic adjustment. And we also think about the lung protective limit as, as my tidal volume set too high or low, respiratory rate set too high or too low. And that's all inputs by the operator. It doesn't change when the lung mechanics change. And does this mode allow for automatic adjustment of tidal volume? And it doesn't. There's nothing automated about this mode at all. It's all user input.
With our second goal of mechanical ventilation, patient comfort, our main objective is to optimize patient ventilator synchrony. With optimizing patient ventilator synchrony, we also have 4 aims. The first is to maximize the trigger and cycle synchrony. Second, maximize flow synchrony. Third, coordinate ventilator output with patient demand. And fourth, minimize auto-peep.
Does your mode allow for the coordination of mandatory and spontaneous breaths? Are all breaths spontaneous with patient effort? And is trigger or cycle based on signal representing chest wall or diaphragm movement?
Looking at the first aim with patient comfort, does the mode maximize trigger cycle synchrony? Now, one of these functionalities is, does it allow for the coordination of mandatory and spontaneous breath? To see this, let's make my patient spontaneously breathe. And right now we have a fixed flow rate, and if I look at my IU ratio, it's approximately 22 liters per minute. I have a fixed tidal volume and I have a fixed respiratory rate. So I'm going to have a fixed I time based on this IU ratio. So I have an inspiratory time of 1.7 seconds. So I'm going to now have my patient breathe. I switch the strength to 3 and we're going to start having some spontaneous breaths. So we notice our breaths. There's a mandatory breath. There's a spontaneous breath there also. So the patient's allowed to spontaneously breathe, but they cannot set their own inspiratory time or their tidal volume either. So it does not allow for the coordination of mandatory and spontaneous breaths. Second, does this mode have the functionality that all breaths are spontaneous with sufficient patient effort? So when the patient starts triggering breaths, do all the breaths turn into spontaneous breaths? And I started to have the patient breathe. I have my mandatory breath. I have a spontaneous breath. But as you notice, there's another mandatory breath. So not all breaths are going to turn into a spontaneous breathing pattern. So it does not have this functionality either. I would just like to contribute my thoughts on patient comfort also. So this is not associated with the paper at all. It's through my own work. When I think of using a mode of ventilation in patient comfort, I think about how many asynchronies are associated with a certain mode of ventilation. And is volume control CMV with dual targeting more synchronous than, say, volume control CMV with set point? And one thing that's not pointed out on the paper is that this Pmax setting or the pressure limiting allows for better synchrony with cycling, and I'm going to get more into that. And it's not automatic or anything. It's still based on operator input. So that's why it's a little off the paper, where the paper is more as, does the mode of ventilation automatically do this? It doesn't need a practitioner or bedside. But this kind of showcases why we still need respiratory therapists and why we still need people at bedside to see these asynchronies, recognize them, and actually change these inputs or these values. So example is, does my breath prematurely cycle? One is, say my patient's compliance changes. And what it's going to do is it's going to hit this Pmax value. And with a high pressure alarm, it's just going to end the breath. It hits this, it's going to open up the exhalation valve, it's going to end the breath. But as you notice, what the pressure limiting does though, is it just limits that pressure. However, it keeps the same inspiratory time. So the patient gets more of a delivered breath than it prematurely ending. And I'm going to show this in a couple more slides. Now, dual targeting may prevent or decrease the incidence of premature cycling compared to a set point targeting scheme, especially a volume control scheme. And here's my example here. I have a screenshot from actually a Draeger, a Vita XL, and this screenshot actually shows premature cycling. And premature cycling is also known as premature termination or short cycling. And it occurs when the ventilator breath cycle ceases abruptly, while the patient requires a longer inspiratory phase. And it's usually attributed to a pressure overshoot, which causes the breath to cycle off when it hits the alarm limit. And here's my example. So we can look at our waveforms. Okay, at the top of the screen you notice a blue waveform, and my blue waveform is my pressure waveform. And this is actually volume control CMV with set point targeting, and it doesn't have the dual targeting aspect. So the patient's breathing, here's a breath here. Here's a breath here. And as you notice, we start to have some pressure overshoots. The patient's meeting my high pressure alarm threshold, and the breaths are starting to premature cycle. And I have a phase where the patient premature cycles these 3 breaths here. And as you notice, if we look at my corresponding volume waveforms, which are at the bottom of the screen in green, as you notice, that volume is significantly different. And that might be very uncomfortable for the patient. As you notice, we have these extremely low tidal volumes now. And now let's take a look at what the actual Pmax does, or the pressure limiting or the dual targeting scheme does. Okay, these slides show kind of the progression of Pmax, and this is volume control CMV with dual targeting, or the Pmax is initiated. This is still a Vita XL. And what I have here is, we want to look at my tidal volume, and we're also going to look at my pressure, okay? And see, this is the first progression. And then what I did is, so I froze the screen for a background reference. And as you notice, that's my initial breath phase in the back. And it's in gray, so we can compare the patterns and the breathing patterns also. And if you see, you notice my peak inspiratory pressure in the top right-hand corner is starting to climb. And as you can see, my breaths are starting to look a little different here. And now let's go to the third screenshot. And as you notice, now my Pmax is going off. And now as my breath, it starts turning into a pressure controlled breath. And it's first initiated here, and here is it squared off, so my pressure limiting has been met. You notice that my peak pressure is now 37. That was all operator input. However, it had a very little effect on my tidal volume, because what it did is it didn't prematurely end my breath. It was for the same inspiratory time. My flow starts to accelerate it, and I don't have that low tidal volume. So with dual targeting scheme, it may reduce these incidences of premature cycling, or it might be a little more comfortable for the patient. So that's one thing to consider.
Does your mode provide unrestricted inspiratory flow?
The advantage of having unrestricted inspiratory flow is the reduction in flow asynchronies. Flow mismatch results when the patient's respiratory drive increases and the fixed set flow rate cannot provide enough assist to meet the patient's demand. This is a screenshot of flow mismatch. And it's easy to identify with the ventilator waveforms. We can look at this blue pressure waveform. And during this inspiratory phase here, the patient does not have a flow, and you can see this is easy to identify with pressure scooping. So I have this fixed constant flow rate, which results in this pressure scooping. So it's not enough flow for the patient's inspiratory demand. And I'm going to disagree with authors that volume control CMV with dual targeting provides unrestricted inspiratory flow. So I'm going to give examples of this by looking at pressure control itself. Now, I did state one of the advantages with dual targeting is that it changes the breath from a volume control breath to a pressure control breath. And with volume control CMV dual targeting, the pressure limiting is kind of a pseudo pressure control breath. Okay, when we think about pressure control, we have a fixed pressure. and we have this fixed pressure waveform, so that's our constant. Our pressure is always constant based on operator input, and then what varies is actually the flow rate. So if the patient's flow rate is low, I might have a small waveform, and if the patient has a larger inspiratory demand, they have a higher inspiratory flow rate. So this is variable based on the mechanics of the lung and actually the patient's inspiratory effort. Now I'm going to try to make my argument and where I disagree with the authors on how a volume controlled CMV with dual targeting provides unrestricted inspiratory flow. I stated before that the breath starts out as volume control, and what I have in my drawing here is this is actually going to be my pressure limiting setting right here, this yellow dashed line, and this is my pressure waveform, and this is my flow. So I have a constant flow because it's starting out in volume control. And then my next breath, say that my patient's coughing or lung mechanics change, and then what happens is the breath starts increasing. I mean, not the breath, but the pressure starts increasing. And what you'll notice with the flow, and I'll show this in the simulator also, actually the flow rate is staying pretty stable because I haven't hit this pressure limitation yet. It hasn't really changed my breath to a pressure controlled breath. And then you'll see a breath, and then it will be a pressure limitation breath. And then what my flow starts to do is during this breath, you'll notice, and it starts to look like a pressure controlled breath, and it starts to decelerate. However, this is pressure limitation, and this is only one component of pressure control, because what you'll see is if the patient's drive changes and they become more vigorous, well, to get the target tidal volume you have set, it takes a lot less pressure, and what you'll see is actually pressure scooping. So the pressure waveform never meets this pressure limiting, so it doesn't change it into pressure controlled breath. So my flow rate is not variable at all. It just stays the same. It's going to still be a constant flow. And the pattern's not going to change at all. So it does not provide this unrestricted inspiratory flow, and it still can lead to flow mismatch. And let's look at that in the simulator itself. Now we're back to my simulator, and as you notice, we're in volume control CMV, and my Pmax is set around 30, or my pressure limiting, and I'm going to show this that you still have flow mismatch, and you do not have an restricted inspiratory flow during the inspiratory phase. So I have my curve set up, so I have this nice volume waveform, and now I'm going to make my patient breathe. So I'm just going to increase the strength to 3 and just make the disease process normal. And as you can notice, at that low flow rate, so the patient's, there's a mandatory breath, there's my spontaneous breath, I have this flow scooping here. I never have the pressure rise to turn it to a pressure controlled breath. And if I look at my curves, I still have a fixed flow rate of 20. So here's my flow waveform. I don't want to go back and show you that it didn't increase. I'm just going to turn this off again. I'm going to turn this back to 0 so the patient's not breathing at all. And if we go back to my curves, I can look at my, let's just go down to my I ratio, and that will show me my, and as you notice, my flow rate is set 19, approximately 20. Now let's go back to my waveform curves. My big waveforms, you notice my flow rate is 20. And now I'm going to make the patient spontaneously breathe again. And as you notice, my flow rate still stays fixed at 20. And then if we notice our volume curve, that will have this little flow mismatch because it's not enough flow for the spontaneously breathing patient. So I argue that volume control CMV with dual targeting does not allow for unrestricted inspiratory flow. There's other modes, but they're not volume control that are dual targeting that does provide this unrestricted inspiratory flow rate. And as you can notice, at that low flow rate, so the patients, there's a mandatory breath, there's my spontaneous breath. I have this flow scooping here. I never have the pressure rise to turn it to a pressure controlled breath. And if I look at my curves, I still have a fixed flow rate of 20. So here's my flow waveform. I don't want to go back and show you that it didn't increase. I'm just going to turn this off again. I'm going to turn this back to 0 so the patient's not breathing at all. And if we go back to my curves, I can look at my, let's just go down to my I ratio, and that will show me my, there we go. This is going to show me my flow rate. I'm going to hit that, and as you notice, my flow rate is set 19, approximately 20. Now let's go back to my waveform curves. My big waveforms, you notice my flow rate is 20. And now I'm going to make the patient spontaneously breathe again. And as you notice, my flow rate still stays fixed at 20. And then if we notice our volume curve, that will have this little flow mismatch because it's not enough flow for the spontaneously breathing patient. So I argue that volume control CMV with dual targeting does not allow for unrestricted inspiratory flow. There's other modes, but they're not volume control that are dual targeting that does provide this unrestricted inspiratory flow rate.
Does your mode allow for automatic adjustment of support to meet patient's demand? And does it automatically adjust the support to maintain a specific breathing pattern?
Let's look at another aim in patient comfort. Coordinating ventilator output with patient demand. After reviewing the last scenario, we can pretty much predict that volume control CMV with dual targeting does not provide this. The way these are presented is from a lower level of automation to a higher level of automation. And if the device, or not the device, but the mode does not allow for this lower level of automation, it probably doesn't have a higher level of automation. And one of the things we look at is if the mode provides a automatic adjustment of support to meet patient demand. And we're going to kind of get more into this. I didn't present this in the first introductory video, but what this deals with is the inspiratory phase of the patient. So that part of the breath phase, specifically with flow asynchronies. And this is looking at driving pressure. So we might have the ventilator, or the ventilator mode itself might provide unrestricted inspiratory flow, but there's still a issue with driving pressure, and that's related to, you can only get so much flow based on a driving pressure. So you can still have asynchronies with driving pressure in a pressure control mode if the driving pressure is too low for the patient's inspiratory demand. So a peak pressure of around 15 to 20 centimeters of water is generally needed to provide a significant support if the goal is to minimize patient work of breathing. And you usually have a fixed level of pressure control. So when we ask if the mode can provide automatic adjustments, so what the mode is actually doing during these high demands, that the ventilator is actually increasing the pressure control output to meet the demand. And as you notice, what I have here is an example of a synchrony where the driving pressure is too low. So they're in a pressure control mode and the pressure is fixed. However, the patient's demand gets high enough where there's still need more of a higher inspiratory flow, and that's evidenced by this scooping in the flow waveform. And as you notice, the flow waveform normally fully decelerates, and here it goes and it scoops again and it does not fully decelerate. So that's what I mean by, does the mode itself provide these adjustments in pressure to meet patient's demand? And of course it doesn't. The next is, does the mode have the capabilities to provide automatic adjustment of support to maintain a specific breathing pattern? And the only way it can do that also is to titrate the level of pressure control of support. And as you notice, it's a volume targeted mode, and the pressure is variable. It doesn't have a set pressure, and it doesn't titrate these pressures up and down during these inspiratory demands.
Can your mode automatically limit auto PEEP?
Our last aim in patient comfort is to minimize auto PEEP. And does the mode actually provide an automatic limitation of auto PEEP? And let's look at it. And I have a fixed respiratory rate around 12, and I'm going to increase the strength to 3, and let's make the patient start tacking out. And we're going to increase their rate to 20 also. So as you notice, my inspiratory time does not change. I have this still the long inspiratory time. It's fixed. The ventilator's not changing it, and automatically that you can see with the flow waveform, it doesn't return to baseline, which is evidence of air trapping or dynamic hyperinflation or auto PEEP. So volume control CMV with dual targeting does not provide automatic adjustment to prevent auto PEEP.
Regarding the third goal, liberation, can we optimize the weaning experience? Does your mode provide an automatic reduction in support in response to increased patient effort? Does it allow for a ventilator-initiated weaning of support? And does the ventilator recommend liberation?
This brings us to our last goal of mechanical ventilation liberation, and our objective of optimizing the weaning experience. And our aim here is to minimize the duration of ventilation. And if volume control CMV with dual targeting does any of this or has any of these capabilities. And one is the automatic reduction of support in response to the patient respiratory effort increasing. So let's look here, and I'm going to increase the strength to 3 and the rate to 12. And as you notice, it's still giving these volume control breaths. It's still trying to give the same volume in the same amount of time. So there's no reduction of support. And does the ventilator provide any ventilator initiated weaning of support? And as you notice, it doesn't. They're still all mandatory breaths, even though the patient's triggering some of the breaths, and there's not a reduction in respiratory rate or the support itself. And if it doesn't do any of this, of course, it's not going to recommend liberation, which is a higher level of automation. How does volume control CMV with dual targeting stack up? First category or goal of mechanical ventilation is safety. As you notice, the only advantage it provides is the manual adjustment of the minimum minute ventilation parameters. Comfort, 0. And I'm going to put a star by that because the authors state it provides unrestricted inspiratory flow, but as you can see by my example, that it does not. It's a pseudo pressure controlled breath. Of course, it changes to a pressure controlled breath for the pressure limitation. However, during a high inspiratory drive, it does not. The flow is still fixed. It never meets that pressure limitation, and the flow does not change. So you still have discomfort and flow asynchronies. And lastly, with liberation, there's no automation with this mode. It's pretty much all tactical, all operator inputs. So there's no liberation. So it provides not much advantages over your traditional volume control mode. However, I would argue that it does provide safety. One factor you can look at is, this is my own star, is that with this pressure limitation, two things. One is safety. If the operator sets it correctly, I have the safety where you're not going to have barotrauma because the pressure is not going to get so high. One, and then with patient comfort, you should have less short cycling because the pressure limitation prevents the breath to cycle off too early. I would actually consider this a 1 if we look at asynchronies, but that's not my criteria the paper was based on.